My name is Varun Dutt, and we are continuing in this lecture in Large Applications Practicum course, understanding how Bison works with Flex. In this particular lecture, we are going to look at how a calculator application can be created using Flex and Bison. This was also one of the activities or challenges I gave you in the last lecture. Looking from the last lecture, we will look at a Bison file which can be used towards the calculator application using context-free grammar. So in this case, the rules section of the file, we have already looked at the declaration section of the file where we defined certain precedences and certain operation and tokens, and also stdio.h as an include file. Now in the rules section of the file, we are going to create context-free grammar rules, which is going like exp can be a factor, or it can be expanded as exp add op factor, or it can be expanded as exp sub op factor. If it's a factor, then $1 refers to this factor. $$ is a variable in Bison, which allows us to capture the non-terminals. In this case, $1 refers to this exp and $3 refers to this factor, and we are basically summing the two. And in this case, the same way we are summing the two. And remember that in this case, we are writing context-free grammars and we are trying to print the value of $. Okay, and generally a rule ends with a semicolon. Then factor can be a term, or it could be a factor mul op term or factor div op term, and you can see that if it's mul op, then we multiply $1 with $3 and store it in $. In contrast, if it is div, it is $1 divided by $3 and semicolon. And then we have the term, which could nothing be but a number, or it could be a bracket open exp bracket close, where we want to take $2, which is the exp part out of it. So, and we assign the number to $, to y by L val. So, in this case, these symbols represent ORs, and in action part, the left side of the rule is referenced by $, and the right side is referenced by $1, $2, $3, etc., as I have shown you. So this is the context-free grammar in the calculator example, which allows me to do addition, subtraction, multiplication and division, including expressions which can be mentioned in the brackets. So the subroutine section contains the definition part of the code in Bison, and this section is copies as it into the generated parser code. You can actually say y by parse returns the value 0 if the input is parses is valid according to the given grammar rule, and it returns a 1 if the input is incorrect and error recovery is impossible. So in this case, we are expecting a 0 to be returned if it is parsing it correctly, and generally this is written as int main y by parse, which will invoke the Bison program and return 0. So combining everything, we have now separately covered Flex and Bison, and now it is to combine them to generate the complete expression parser. For that, we need to know how Flex and Bison interact with each other, and the answer is simple. The YY parse in Bison will call the YYLex every time it needs a new token, and since YYLex returns a token, Bison needs to know what that token is, and this is how we do it. So typically we have in the Bison file token definitions, which we have already seen in the definition part. When Bison file is translated with a Bison -d flag, which we will shortly see how to compile a bison.py file, a header file with the name filename.tab.h is created and has definitions like define num 258. This is the file that can be included in both the Flex and the Bison specification, and this Flex file can then call then return num, and the Bison programs can match on this token. So this is the idea that how the Flex and Bison files can communicate with each other. So for example, for the calculator example, this is the Flex file where we have included the same fb1-5_varun.tab.h. This file will be created by Bison. We have included it in the Flex program, And then we have written the rules, which is just to create tokens out of addition symbol, subtraction operation, multiplication, division, bracket open, bracket closed, and numbers. There we are going to convert that number into y by l val and return that number. Backslash n means end of line, and end tab is ignoring the, doing nothing. And at the same time, we also have anything else, we will write it as mystery character and print it. So in this case, this is the Bison program corresponding to the flex file, and you can actually see this is stdio.io.h, and we have already defined these tokens, which we have defined in flex: num, add op, sub op, mul op, div op, abs op, and op cp. Some other tokens, eol, exit. Add op, sub op have left associations from left to right, and they are at one level, and the mul op, div op also have left association from left to right in case of parenthetical operations, and mul op and div op have higher precedence than add op and sub op. And then we write calc list, could be a calc list expression exp eol, where we print $2, which is exp, and exp can be a factor, exp add op factor, exp sub op factor, where we sum or minus. And similarly, we can have mul op term, div op term, factor term, where we can do multiplication and division, and term can be y by l val, or it could be op exp cp with the $, which is exp part. And now we write printf, we write y by parse, and we also create y by error to catch any error if it occurs. So y by parse will call y by lex, and y by lex will give the token, and Bison will try to match context-free grammar rules to the tokens and to be able to calculate the expression for us. Now the question is, how do we run everything? So for that, we can actually create a make file. Going back to lecture 1, there we can write a target, colon, and then the dependencies, which is the .l, and the prerequisites and the .wi-fi. And then the first thing recipe we need to do is Bison minus d and compile the y.wi file, which is the Bison file. Then we compile the flex file, and then we take the cc compiler and we take the object which we need to create, the flex file, the Bison file, and the flex file, which are generated through LFL flag, and be able to execute it. And then we will just, once this is get created, we can write ./fp1-5 underscore Varun, and then run the program and see the calculator in action. So here is an example. We are already here and we have run this file, and you can see I'm writing an expression and it's giving me an answer correctly. 5 plus 6, 11, 4 by 4, 1, and 4 divided by 2, 2. So this particular calculator works. So Flex and Bison are really very powerful tools for scanning and parsing input. You can create different types of applications using Flex and Bison, which could also be towards compilers, which are really large applications. There are other parser programs also available like NPTEL and Java CC. You can also try these and Google and check them out. So Flex and Bison was prepared using this resource by John R. Levine. I acknowledge the TA for the kind help. And now is the time for activity, where we are going to use the activity of the calculator which we created in the last lecture and this lecture, and build upon it to add power and log 10 operations to extend the calculator. So now what we want to do, we need to define a POW or power operation, where we can say 2 raised to the power 3 will be 8, and 2 raised to the power 2 raised to the power 2 will be 16. So right associative we can create. So it will first solve this part and then it will solve this part. So associativity is the direction in which calculation proceeds. And log would work like this typically: log 10 to the base 10 1, log 100 to the base 10 100, to the base 10 is 2, and remember, only inputs that are multiple of 10s are to be entered right now. Okay, and log will have the highest, followed by the power and other operators which they exist. So we'll have to define power operator and the log operator as two other in the list of operators which we define in the Bison program. So I would request you to try this activity and try it out on your own, extending the calculator program and getting acquainted with Flex and Bison. See you in the next lecture. Thank you.